So hello everyone. What I'm going to talk about today is some work I've been doing with some colleagues in Brest, Jonathan Gula and Guillaume Roulet, and it's about internal tides dynamics over the North Mid-Atlantic ridge. So just as a brief reminder, what are ocean internal tides? So these are ocean internal waves that are being specifically generated by the interaction between the large-scale astronomical or barotropic tide and the topography. So this is a schematics of what it looks like. Basically, you have here you have a large-scale flow that is going back and forth over a small topography, and you can see these internal waves beams that are being generated. And here is another look at it from the surface, from actually a satellite altimeter in the ocean. And you can see the surface pressure perturbation that is induced by tidal beams that are that emanates from the Hawaiian ridge. So this is from data, but in the study I've been using what we call realistic numerical simulation. So it's high resolution compared to like a general circulation model, meaning that it solves the Boussinesq hydrostatic equation with a typical horizontal resolution of 2 kilometers in this case, and we basically have a few hundred of vertical levels. And it's realistic because it has atmospheric forcing, so it has also the mesoscale and stuff like that. And this animation, I hope you can see it correctly, this animation shows the pressure perturbation at the tidal frequency, so it's the pressure perturbation induced by the internal tide field. So it has atmospheric forcing, it has tidal forcing, and the internal tide field, and it also has a realistic topography. Okay, so in this movie we can spot the like a prominent internal tide generation spots, such as here around the Azores Islands, and we can also see that this internal tide field is made of long-range propagating internal waves. And so as these internal tides propagates in the ocean, they can be affected by a whole kind of mechanism and processes. And we've been discussing about some of these mechanisms earlier in this meeting. And all these mechanisms in the end, and the life cycle of the internal waves in the end is that it should be dissipated. Because for the internal tide, you are constantly forcing your internal tide field with the barotropic tide. And so in the end, you must have a dissipation of energy, because we know that the internal tide field is in a stationary, statistically stationary state. And so this dissipation occurs at small scales. And here you have a map of an estimation of this dissipation of internal tide in the world ocean. And when it occurs, this dissipation, it will trigger mixing, which is very important for the global ocean circulation, for transport of heat and biogeochemical matters, and in the end for climate and the climatic role of ocean. And so this brings me to my main motivation, which is that we need to better understand the internal tide and its impact in the ocean. And to do so, we need to better understand and characterize the life cycle of the internal tide from generation to dissipation. And so my talk here is about one particular mechanism that affects the internal tide. And this mechanism is topographic scattering, which is exchange of energy between the different scales of within the internal tide field that is being triggered by interaction with the topography. And the main message that I will show in this talk is that topographic scattering can lead to substantial dispersion and dissipation of the internal tide field. And I will show this over the North Mid-Atlantic ridge, but this result is fairly it's applicable to the global ocean. And so to show this, I will using another numerical simulation. Actually, it's a regional numerical simulation. So the strategy here, and I use a different model, which is Croco. So for those who do not know Croco, it's a kind of a French flavor of Rom's model. And so the strategy we've been using here is a grid nesting approach. So we start with a coarser resolution over the whole basin. And then you use this realistic field to force a numerical simulation with a smaller domain that is being shown here in black. And in this smaller domain, you have a higher resolution, and you do that twice. And in the end, we have numerical simulation in a domain that is centered around the Azores Islands. And it's 750 meter horizontal resolution. And in this subdomain, we have a tidal forcing so that it will develop an internal tide field, because you have a topography which is made of the North Mid-Atlantic ridge that crosses the domain, as shown here. And you also have the Azores Islands here and a few isolated but very steep seamounts that are visible here. And so in addition to this realistic numerical simulation, I also run some kind of semi-idealized, let's say, simulation, where I do not put the mesoscale field, but we have I use a flat stratification, which is actually the horizontal average of the realistic stratification, and I perform a tidal neuron to investigate the tidal dynamics apart from other phenomena. So let's jump into it. So we want to investigate the life cycle of the internal tide. So first thing to do, first thing we did is to first decompose the barotropic part, so what is vertically homogeneous, and the baroclinic component of the tidal field, so field at the tidal frequency, and use as a framework to analyze data the linear boostiness equation, from which you can form this kind of equation for the vertical integral of the energy. And so it's a kind of a conservation equation, where you see that you have here a term which is a conversion from the barotropic tide, and it's given by this. Here you have a product between the barotropic tidal current and the gradient of the topography and dissipation. And this is all assuming that nonlinear terms are not being very important here. And so here is a map showing what the distribution of this energy looks like. So you can see that you have a lot of wave activity around the islands, around the seamounts, in between them, and also all over the ridge, basically. And you can also look at the fluxes and the divergence of the energy flux. And you clearly see some major site of generation around the seamounts, sorry. And fluxes of tidal energy flowing away from these seamounts. So this is just to get a qualitative picture of the tidal energy activity. And now if we take this equation and do time average of this equation, and because we have an internal tidal field that is in a statistically stationary state, then we end up with this very simple equation describing the life cycle of the internal tide. And we can quantify what are the magnitude of these different terms. And what we found is that if you take the average over the whole domain, the amount of energy, of internal tide energy that is being dissipated within the domain is actually 80% of what is being generated. So in blue here, we have the generation, and dark blue is what you want to look at. That's how we measure it directly in the model. And red is the dissipation. And you can see that, relatively speaking, dissipation is quite big. And it's even more interesting to look at this kind of diagnostic in subdomains. And these subdomains are shown here in red. And we can contrast, for instance, between the subdomains around the seamounts, where this fraction of dissipated energy is smaller. It's like 50% over the domain, and it's actually down to 30% locally. So if you look at very small domain, just enclosing the generation site, dissipation is 30% of the generation. And this number, 30%, is actually what we use when we want to parameterize this effect in a general circulation model of the ocean that do not include an internal tide field explicitly. And compared to this to this lower value, on the contrary, if we look at the ridge, so any of this subdomain here, and this is being shown here, you can see that the red bar is of the same magnitude as the blue bar, and that actually we have all the energy that is, well, the dissipation is the same amount as the production from the barotropic tide. So we wanted to understand a little bit what was going on, and we went further in the analysis by further decomposing the baroclinic tidal field into vertical modes. So vertical modes can be seen in this context as a scale separation in the vertical, using a set of modes that are being defined by this standard Sturm-Liouville problem, which depends on the stratification profile. And so this picture here shows basically what we are doing. You're using this set of mode to decompose this kind of signal, and this is in an idealized setup. So we solve the vertical mode, we project the dynamics onto it, and this is typically what you observe if you look at the horizontal structure of the modal amplitude. This is back in the first numerical simulation I was showing you. So mode 0 is basically the barotropic mode, so that's what we call the astronomical tide, so large scale basin mode. And then you have the baroclinic modes, and the higher the mode number, the smaller the typical horizontal scale that is being associated with this mode. Okay, and that will be this characteristic will be important in the following slides. So you can repeat the same kind of analysis. You can derive in a linear framework, you can derive the energy equation per vertical mode. And you can see that we have a conversion term here that can be seen as kind of a generalization of the conversion from the barotropic to the baroclinic tide. But now we have conversion between of energy or transfer of energy between each mode that is being contained that is being described by this term. And this term involves a bilinear product of the pressure in one mode and horizontal current in another mode times the gradient of the topography. And so particular cases are if you take m equals 0, then you have the conversion from the barotropic tide to any mode number, n. And if you take greater to 0, then you have the scattering or energy exchange between baroclinic modes. And so we measured this conversion term and take the horizontal average of it in our domain. And this is the result you obtain. And I only show the upper right triangle because this matrix is antisymmetric. And so what you can see here is first line is the conversion from the barotropic tide to each mode number. Okay, so it's clearly a dominant mechanism. And then second and so on other rows account from a transfer from mode 1, mode 2, etc. to higher modes. And so what we see is that this transfer of energy is not negligible compared to the barotropic tide. Okay, it's smaller, but yet it's important. And also we can see that it's red everywhere, meaning that, and what that means is that one given mode on average gives energy toward the higher modes. So that means that in average, we have some kind of cascade of energy that goes towards higher modes, meaning that it goes toward a smaller scale. So it's kind of a forward energy cascade. We can further look at the different terms here to get a broader picture of what is going on here. So dark blue is conversion from the barotropic tide. Light blue is baroclinic scattering. And so we see that you have baroclinic scattering that is the loss of energy for the first three modes, and that transfers this energy to the higher mode. And you also see that if you look at high modes, the total conversion, the total input of energy is roughly the same as the dissipation, right? So you have more or less 100% of the energy that is being injected into this high mode that is being dissipated. And this fraction is actually smaller for the low modes. So that explains why this kind of scattering catalyzed by the topography to the higher modes results in a higher dissipation than expected, meaning higher than 30% in my case. And so again, we can look at the different, the contrasting subdomain I was highlighting before. And you see that if you look at the seamounts, you have baroclinic scattering that is, relatively speaking, less active compared to the ridge subdomain, where you have a very strong, very active baroclinic scattering. For the mode 1, for instance, the input of barotropic tide is almost completely lost by through baroclinic scattering. And furthermore, an interesting fact is that over this region, the reach 2 domain, so which is here, you actually have dissipation that is greater than conversion from the barotropic tide, because you can see that you have a weak negative flux here, which is actually in the first mode. And what that means is that over this subdomain, you have some incoming mode 1 flux from outside the domain that is then being scattered toward higher modes within the subdomain and then and dissipated locally. Okay, so that brings me to my conclusion. What I showed is that based on realistic high-resolution numerical simulation, what we observed is a fairly high ratio of dissipation over conversion from the barotropic tide in the domain, that this relative dissipation is geographically variable. And what we showed is that this high dissipation is actually favored by scattering from the topography that transfer energy toward higher modes and smaller scales and results in an enhanced dissipation within the numerical domain. Okay, so I will stop here and thank you for your attention.
Thank you very much, Noé. So, is there any question? Everybody would like to have lunch or dinner, depends. Okay, there is no question, so we said. There is a question by Yoei. Can you see it, Noé, in the chat?
Yes, direct dissipation from the first mode looks so high. Is the dissipation caused by basic harmonic viscosity? I have no clear answer for that, because it's true that it's kind of high. There is no harmonic viscosity, but there is a parameterization of the, in this kind of model, what you use is parameterization for the vertical shear and stuff like that. So the vertical component of, well, the dz of kappa, dzu and stuff like that. And so I think in this case, it can be either this parameterization, and more especially what you have near the boundary layers, where you have an enhanced dissipation that will act on all modes, I guess. And so this kind of boundary, KPP dissipation in the boundary layers plus drag can be responsible for this higher dissipation in the first baroclinic mode already.
Noé. There is a question by Adele.
Yeah, is there a difference between hydrostatic and non-hydrostatic computation? So we did not run a non-hydrostatic simulation for this case, but as far as I know, you would not have any difference between. We are not looking at scales that are small enough. So some colleagues at LUPS, maybe you know them, have been running, like trying to run non-hydrostatic numerical simulation of this kind of problems. And it's really when you start to resolve smaller scales compared to our horizontal resolution. So I mean, we have a 1 kilometer horizontal resolution, right? And basically, if you don't go like below 100 meter horizontal resolution, non-hydrostatic effects are not dominant for this kind of dynamics. Also because the frequency is not that high compared to the Born-Weisel frequency, right?
Okay, thank you, Noé. So if there is no other question, there is a question by Mani.
Oh yeah.
You see?
So I have to read it. Maybe I missed it, but do you observe subharmonic and superharmonic frequencies? The different modes are at what frequency? So yes, we do observe superharmonics. Not so much. We also observe subharmonic, but they're kind of weird because they are trapped, because subharmonic are below the Coriolis frequency in this region. But we do observe superharmonic frequency, but everything that I've been presented is from time-filtered films at the dominant tidal frequency, the semi-diurnal tidal frequency. So I'm not, all the modes that I'm showing are at the semi-diurnal frequency, not at the superharmonics.
And there is another one.
As the simulations are realistic, could there be contribution from near inertial modes? So that would be nonlinear, which I have not been looking at that precisely. And also the simulation is realistic, but it's far from perfect. And in this simulation, we were using atmospheric forcing that was, if I remember correctly, it was daily atmospheric forcing. And that is not a high frequency enough in the forcing so that you generate a very intense near inertial wave field. So the near inertial activity in this simulation is quite low compared to what you would expect based on observation and stuff like that. So I think the contribution of near inertial waves that are being forced at the surface is quite negligible in my simulation. But then you can have specific near inertial motions near the bottom, and there has been quite some literature about that. Probably that could be an effect, but I don't know for sure, and I've not looked. I haven't looked at that.
Okay, thank you, Noé. So maybe we can stop here.
Yes, thank you very much.